Hello and welcome back. Into 8, we get to work with square root equations. So first, a quick definition. So square root of a number n is any number that equals n1 squared. So for example, negative 5 squared is 25, positive 5 squared is 25. So negative 5 and 5 are square roots of 25. Now, when we use the radical symbol, this is a radical. When we use the radical symbol, this implies we want the positive or principal root only. And of course, the special case, or 0, for the square root of 0. Now, we've seen before when we see radicals, it's possible that they are irrational. It's possible that they are also rational. So, for example, square root of 7, we don't have any nice, neat, pretty integer that I can multiply by itself to reach 7. So this is in the set of irrationals. For the square root of, let's say, 9, we'll simplify down to 3, so that is in the rationals. Also happens to be an integer. Also happens to be a whole number and a natural number. Yes, a lot of hats on that one. And both of these, of course, are also in the set of reals. However, if we do, say, the square root of, let's say, negative 2, this one kicks us out of the real numbers. I can multiply two positive numbers together to get 7. They just have to be irrational numbers. To get to a negative 2, a positive times a positive kicks us over to a positive. A negative times a negative would also kick us over to a positive, and 0 squared is 0. There is nothing in the set of reals that will allow us to square it to reach a negative number, so this is non-real. So it is possible to get kicked completely out of the set of real numbers when there are square roots involved. Now, as long as we're listening to this implication that we have the positive root only, then we can work under the assumption that if we have the square root of, let's just say, a smiley face squared, that the square and square root are basically undoing one another. And we get whatever the argument was inside. So these are considered inverse operations. Again, assuming that we're working with the implication that we want the principal root only. So one other quick caveat that we need to look at before we get into the actual problems. The solutions to A equals B are a subset of solutions to A squared equals B squared. So it is possible that we will have solutions that look good for everything after we square it, but don't work in the original. So it's possible that this will have solutions that A equals B does not. Now, our general strategy for this is going to be a little bit similar to what we did in absolute values. So is the radical alone? If it's not, just like with the absolute values, fix it. Once it's yes, we undo. Right now, in this course, we're only working with square roots. There are other types of roots than square roots. There are cube roots, fourth roots, etc. We're only working with square roots. Undo the square root by squaring both sides. Solve the resulting equation. In this one, written in stone, not just a good idea like it is with linear equations or even with quadratics. Required step, must do. Check. And anytime you check, remember it must be in the original. The reason that we're checking is that we might get extraneous solutions. Then we go to our solution set. And if necessary, Euler diagram. So this one, don't forget, highlight it, write it down in red, underline it, do whatever you need to do so that you remember you must do this one every time. It is required. Will you lose points if you don't? Yes. Do we have to do it on everyone? Yes. Make sure you check every single one of these square root problems. You can run across extraneous solutions. All right, so let's run through a couple of these together. So we'll start with the square root of 5x is worth 15. So the radical is already by itself. So we can undo the radical by squaring both sides of the equation. Square and square root, remember those are inverse operations. So left-hand side I have a 5x, right-hand side I have 225. Then we solve the resulting equation. This one happened to be linear. So we'll multiply both sides by a fifth. So So 1 times x is worth a fifth of 225, so that'll go in 4 times, 2 left over, 45, so x is 45. Step 4 required, don't forget. Always checking in the original. So all of the variables turn into parentheses. Everything else comes along, and we're using a question mark above the equals since we don't know necessarily that they are equal. We're just checking to see, are they equal? Since we don't know necessarily that this is an equation, we can't use the properties of equality. We just have to simplify each side. So we have one set of grouping symbols here. We have an operation under the radical. So that's our grouping symbols. So even though they didn't write them down for us, we treat it as if there were a set of grouping symbols around that. So 5 by 5 is 25, regroup the 2. 5 by 4 is 20 plus 2, 22. And we want to know, is that equal to 15? You do have to bring down both sides until you have just one number per side. Square root of 225 is indeed 15. 15 equals 15. Does work out. So then in our solution set, 45 is our solution, not the 15 that was on both sides, but what value the variable took on that worked in the original, and that was 45. Okay, so let's try another one. Couple more steps, but same ideas. So we're going to solve the square root of the difference of 3x and 2 is worth 4. So step 1 is already done for us. The radical is by itself. So step 2 is where we'll jump in. We will square the left side and square the right side. Left-hand side, square and square root are inverse operations, so we're left with just the argument, the 3x minus 2. The right side, we have a nice pretty 16. So this one happens to be linear. So now we're just using addition property of equality, additive inverse, arithmetic, additive identity, and then multiplication property of equality. So 1x is worth 6, so x equals 6. So we have a possible solution. We don't know that this is a solution yet. This is only a possible solution. We have to check. So we copy everything from the original, nowhere else. Always the original, no other steps after the problem that was given to you. So the number we're trying out is 6, and we want to see if this works out. So a couple operations inside of the grouping symbols, so we'll take care of those first. Multiplication before subtraction, of course. And we're possibly equal to 4, square root of 16, possibly equal to 4. 4 equals 4. So you're not done until you have the same number on both sides. This one is true, so we get to keep the 6. Okay, our next one is going to be a little bit shorter, but it does introduce another concept that we'll need. So is the radical by itself? This time, no. So step 1 is fix it. Get that square root alone. So we'll subtract 5 on both sides. So square root of the quantity x plus 5 plus 0 is negative 4. Square root of x plus 5 is negative 4. So here's where we run into a problem with our definition, though. By definition, recall that when we saw this was the principal root. Principal root implies positive. This is a negative. That is a contradiction. Once we get that, if the radical is by itself and a negative on the other side, we can jump right to empty set. You've seen that before in another type of equation. Try to think of what type of equation that was. We saw that before in absolute value equations. By the way, just in case you do end up going onto a different track in math than the one you're currently on, this is not true when we have a cube root or a fifth root or any odd root. This is only true when we have an even root. Now, sometimes they turn linear, sometimes we get something that is nonlinear in nature when we do these problems. So we'll next try out the square root of the quantity 9x, minus 2. We'll just start fresh here. Square root of the quantity 9x minus 2 is worth a 2x. So step 1 is done. The radical is by itself. Step 2, then we undo the square root by squaring both sides. So notice here, I did use the grouping symbols here. That is required. 2x squared is not equal to 2x quantity squared. So these are needed. Those are necessary. So left-hand side, 9x minus 2. Right-hand side, 2x by 2x is a 4x squared. So notice this time, this turned quadratic. Different strategy for quadratics versus linears. For quadratics, we want to set one side to 0. Our coefficient of the squared term is a positive, so I will move these two guys instead. So I'll subtract 9x on both sides. I will also add 2 to both sides. So 0 is 4x squared minus 9x plus 2. So then after that, we're identifying our a, b, and c. So a is 4, b is negative 9, c is a positive 2. So we're looking to have a product of positive 8, a times c, in a way that will sum to a negative 9. If I'm multiplying to a positive, this is either plus plus or minus minus. The fact that I'm adding to a negative says everybody gets a negative sign. So negative 1, negative 8, and we have it on our first attempt. So then 0 is 4x squared instead of a minus 9x, minus 1x minus 8x, and bring down your plus 2. Don't forget, this does have to stay an equation. Hang on to this guy. Don't lose him. Don't lose me. So now we're factoring by grouping. First two terms, I can grab an x, leaving me a 4x minus 1. Second two terms, I can grab a negative 2, leaving me also a 4x minus 1. So then I have 4x minus 1 by x minus 2. Now we have what we want out of a quadratic. We have a multiplication problem ending in 0. Now you can tell me for sure, written in stone, that one of these two is worth 0. So we'll set a 4x minus 1 equal to 0. We'll union that up with the possibility that x minus 2 is our 0. And then we're just solving linear equations from there. So we'll add 1 to both sides. So 4x plus 0 is 1. 4x is worth 1. And we'll multiply both sides by a quarter. So 1x is 1/4. X equals 1/4. Union that up with x equals 2. So this time we do need an Euler diagram. We have something that's not in the set of integers. So our solution set contains the 2 as long as we check it. So let us do the check. And that one will in fact check. 9 by 2 minus 2 possibly equal to 2 times 2. So square root of 18 minus 2 possibly equal to 4. Square root of 16 possibly equal to 4. And 4 equals 4. So it did check out. That's why we got to keep it. Our other guy, right to the Euler diagram. Yeah, cut that off. My apologies there. Okay, so our domain set of integers. 2 is inside of the reals, rationals, integers, whole numbers, and natural numbers, but 1/4 is real and rational, but not in the integers. All right. So next one. Try out the square root of the quantity 3x plus 18 is equal to x. Square root is by itself, so we'll undo the square root by squaring both sides. Left-hand side, square and square root are inverse operations. Right side, x times x is x squared. This one, again, is quadratic. So I will subtract 3x and 18 on both sides. So 0 is x squared minus 3x minus 18. So this time I'm looking for a product of negative 18 and a sum of negative 3. Product being negative tells me I have one of each sign. Sum being negative says the big absolute values get the negatives, little absolute values get the positives. So right product, wrong sum, right product, wrong sum, right product, right sum, and a coefficient of 1 tells us we can do our fast factoring on this. So x plus 3 by x minus 6 is equal to 0. So x plus 3 equals 0, union that up with x minus 6 being 0. And then we're just solving linear equations in one variable again. So x plus 0 could be a negative 3. So x is negative 3, or x is a positive 6. So we check those out. So square root of 3 by negative 3 plus 18 possibly equal to a negative 3. So square root of negative 9 plus 18 possibly equal to a negative 3. Square root of 9 possibly equal to a negative 3. 3 is not equal to negative 3. This is an extraneous solution. So this will work everywhere after we introduce the square symbol. It doesn't work in the original, though. We have to discard it. Next, we check to see if we get to keep the 6, though. And again, always going all the way back to the original to check these out. So simplifying, square root of 18 plus 18 possibly equal to 6. Square root of 36 possibly equal to 6. 6 equals 6. True. So we get to keep only one of our two solutions. We only got to keep the 6. Okay, we'll do one more of these together. I'll have you all try a couple. So we'll try the square root of the quantity 9 plus x is equal to the sum of x and 3. Radical is by itself. Check. Undo the square root by squaring both sides. So left-hand side, a 9 plus x. Right-hand side, I'm going to write out 2 copies of the x plus 3. The reason I'm doing that is I will need to FOIL these. Just a quick little side problem on why I'm doing it this way and why I'm not just saying x squared plus 9 on the right-hand side. Try out 2 plus 3 quantity squared. Try out also 2 squared plus 3 squared. Go ahead and pause it, simplify each of those, see if you get the same number. Welcome back. Hopefully you did not get the same number. 1 is worth 25. 1 is worth 13. They are not equal to each other. So we do have to FOIL that out. So 9 plus x is worth x squared plus 3x plus 3x plus 9. So 9 plus x is x squared plus 6x plus 9. This is quadratic again, so I'm going to move the 9 and the x. So then 0 is x squared plus 5x. So this is solvable by factoring. GCF was x. I have a multiplication problem ending in 0, so either this factor is 0 or the other factor was 0. That one's already solved. This one, we'll just use the addition property of equality, additive inverse, and additive identity. So x is 0 or x is -5. Now we see if we can keep them. Maybe we can, maybe we can't. We have to check. So square root of 9 plus 0, possibly equal to 0 plus 3. Left side is now square root of 9. Right hand side, 0 plus 3 is 3. Square root of 9 is 3. 3 equals 3. That's true. So we at least get to keep the 0. Now we check the other. Square root of 9 plus a -5, possibly equal to -5 plus 3. So square root of 4, possibly equal to a -2. 2 is not equal to -2. This is an extraneous solution. So in our solution set, we only get to keep, in this case, the 0. Okay, have you all try one out. So we'll do the square root of quantity 2x minus 3 is worth the difference of x and 3. So see if you can work through that problem. So student try problem. Okay, welcome back. So our square root was already sitting by itself. Awesome. So then next up, undo the square root by squaring both sides. Left hand side is now 2x minus 3. Right hand side, we have 2 copies of x minus 3. So we'll go ahead and then FOIL those out. So x squared minus 3x plus 9. So 2x minus 3 is worth x squared minus 6x plus 9. This was quadratic. So next up, we'll subtract 2x on both sides and add 3 to both sides. So then 0 is x squared minus 8x plus 12. So here then, this is factorable over the integers. I want a product of 12 and a sum equal to -8, and -2, -6 will get both jobs done. So we set each of those to 0 and solve. So the first one, I'll add 2 to both sides of the equation, giving me x plus 0 is worth 2, so x is 2 is one possibility. Second one, I will add 6 to both sides. So x plus 0 is worth 6, x equals 6. So 2 possible solutions. So then, check. So substitution, where we used to have an x, now we have a set of parentheses. Then we go back through and fill in our possible solutions one at a time. So root 4 minus 3 possibly equal to a -1, square root of 1 possibly equal to a -1. 1 and -1 are not the same. We have to discard the positive 2. Next, we'll check out the positive 6. And again, I'm going along with the original problem only. So we're filling in 6's. So root 12 minus 3 possibly equal to 6 minus 3 is worth 3. Square root of 9 possibly equal to 3. 3 equals 3. That one is true, so we do get to keep the 6. So we had one solution only, the positive 6. 2 was our extraneous solution. Okay. So this should give you enough to work through your problems from section 2.8. I did want to show you just one quick little Euler diagram that your author uses. I don't require it at the end of mine, but an Euler diagram of our solutions, of what's happening here. We have our 6 that worked in both, and we have our 2 that worked only in the square version. So the inner one is solutions to the original. The outer one is solutions to, and I'll just go with the cleaned up version. So both of those are solutions to x squared minus 8x plus 12 equals 0. Only the 6 is also a solution to the original. So that should give you enough to work through the 2.8 problems. If you have questions, please get in touch. Otherwise, I'll see you next time, and stay safe out there.